Hello, everybody. This is lecture 4 of module 2, and I'm your guide Akanksha Singh, who will be taking you through the entire subject of network security and cryptography. We've already discussed a lot of topics in this module. Lecture 4 is in continuation with lecture 3. Without having a well versed understanding of lecture 1, lecture 2, and lecture 3, you cannot understand lecture 4. So, my recommendation for all of you is that before going through lecture 4, please go through other lectures of this module and then come on this lecture. Okay, so in last lecture, we've already seen different topics. In my first lecture, told you, in my first lecture of module 2, I told you what do you mean by abstract algebra, what do you mean by modular algebra. And in my next lecture, I told you about what is modulus. And in my third lecture, I told you about different concepts of modularity. I told you about what is a Euclidean algorithm. Right. So I also told you about GCD, greatest common divisor. And today we'll be discussing the next continuated topic of Euclidean algorithm, which is extended Euclidean algorithm. Now, what do I mean by extended Euclidean algorithm? My This topic of extended Euclidean algorithm is in continuation with the previous topic that we had left in the lecture 3, and today we'll be completing that topic. In my lecture 3, I had talked about Euclidean algorithm, and today we'll be discussing about extended Euclidean algorithm. Now, the extended Euclidean algorithm is an extension, is a pure extension of or pure improvement of Euclidean algo. Right. So extended Euclidean algorithm as is an improvement of Euclidean algorithm. Definitely it is going to find out GCD, as all of us have understood already that Euclidean algorithm is used for finding out greatest common divisor. So my extended Euclidean algorithm is going to find out GCD as well as linear combination. Now this is very important. Extended Euclidean algorithm is very useful for finding out GCD of any two integers along with linear combination. You can find out linear combination of the two integers that is equivalent to the GCD. That is very important. Extended Euclidean algorithm computes greatest common divisor of a comma b, and also helps in finding out a linear combination of a and b, which is equivalent to GCD of a and b. As you can see here, there is an equation written here that will help us in finding out the linear combination of two integers a and b, which is equivalent to GCD of a and b. Right. So this is how you're going to find out the linear combination. Here I have taken up an example which will help you to understand how we will be using extended Euclidean algorithm. See, the question says find GCD of 1180 and 482, full stop. Further, find linear combination of 1180 and 482 that is equivalent to their GCD. Now, see here they haven't mentioned anywhere that you have to use extended Euclidean algorithm. They've just mentioned that you have to find out linear combination of two integers that is equivalent to their greatest common divisor. Now, that is something that you have to calculate, that here since they are asking about linear combination of two integers that is equivalent to their GCD, we need to use extended Euclidean algorithm, and that is the purpose of extended Euclidean algorithm. Okay, so I'll be solving this question so that you can have an understanding of what is done in extended Euclidean algorithm. So let's start by finding out GCD. Right, we've already seen the method of finding out GCD. Start by find GCD of 1180 comma 482, right? So in my last video I told you, whichever is the greater value, please write it down on the other side, and 482 on this side, right? So what to multiply to 482, which will give me equivalent value to 1180, or just the smaller value of 1180. If you multiply this by 2, you're going to get the smaller value, which is 1180, smaller than the 1180 value. Plus if you add 216, it is going to give you the equivalent value of 1180. Then you will be switching this value here, and you will be switching this value here, right? So my 482 will come here, and my value 216 will come here. Now what to multiply to 216 to get somewhere near about 482, lesser near about value uh, than 482, which is, if you multiply it by 2, you're going to get a value which is just smaller than 482. And if you add 50 to it, it is going to be equivalent to 482, and then further swap the values. Therefore 216 will come here, and 216 50. Now what to multiply to 50? You can very clearly see, if you multiply it by 4, you're going to get 200, plus if you add 16, you're going to get 216 value, right? Again perform a switch, 50 will come here, 16 will come here. Now what to multiply to 16? What to multiply to 16, class? Now to 16, if you multiply by 3, you get a value which is just smaller than 50, and if you add 2 to it, you get exactly equivalent value to 50. After which I'll be performing a switch, wherein 16 will come here, 2 will come here, right? What to multiply to 2? Now if you multiply 2 to 8, you are going to get exactly equivalent value, which is 16, right? And to if you are to this, you can add nothing, because it is already equivalent to 16. Therefore you get a value 0 here, as you can see. Therefore you get a value 0 here. Okay, you get a value 0 here, right? There's no issue. Now what to do? What did I say? If you get a 0 value here, this value is going to be the answer of GCD of two numbers, right? So here is the answer, which is 2. Either you can pick up this value, or you can pick up this value. It's one and the same. Okay, so the GCD of these two numbers is 2. Okay, now for finding out linear combination, what do I have to further? I have to find out linear combination of 1180 and 482. What am I supposed to do here? I am going to pick up this equation and write down my values. GCD is 2 here, as I have found out this. And after writing GCD, 1180x plus 482y, right? So this is my linear combination. And here what am I supposed to find out? I am supposed to find out the value of x and y. Okay, so moving ahead to finding value of x and y, this is how you're going to solve it. Okay, now to okay, now my hint is, what you have to do is pick up that equation, pick up that line from these multiple lines that has 2 in it. See here, I can see that this line, let me take another pen so that you can understand well, right? So here, if you can see that this equation has 2 in it, right? So if I modify this equation, how can I write it like this? 2 can be equal to 50 plus 16 minus 3. I have just taken my minus inside. Okay, right? I hope you can understand. If I pick this value and put it here, what it will be? It will be in minus value, right? And it will be equivalent to 2. So 50 plus, or 50 minus 16 multiplied by 3. I've just taken my minus inside. So this is how I've written this equation. Why have I written this equation in this form? Because this is somewhere equivalent to this equation. This side is equal, right? Therefore, I'll be moving ahead to finding out what is the value of x and what is the value of y. So just wait. Okay, see now 16 minus 3 and 50, these are the two values. Whichever is the smaller value, what is the smaller value here? Just see this part, this and this part. uh, Please ignore this part, ignore this part, and then see which one is the smaller value. 16 here is the smaller value, right? Now for 16, find out a substitution from these equations. This is the equation from which you can find out the substitution for 16, right? How you'll be writing it down? Just wait and see. This is the part which is similar. Now for 16, I'm going to write 216 plus 50. I hope you can understand this, right? And to this I will be multiplying by minus 3. Now to solve this, how will you solve this? See, 50 plus 216, if I open this, will come with minus 3 plus 50. I have 4 3s are 12, and since there are two minus, it will be plus. 4 3s are 12, and there's one more 50 here, so that is going to be somewhere 50 13, right? I hope that is what you've got. Now after doing this, again pick up the value which is smaller. Please ignore these values. Which one is smaller? 50 here is smaller. Again for 50, find out a substitution from this. This can serve for substitution of 50, this equation. Now how will you write this? 216 minus 3 plus, for 50 I will be writing down as 482 plus 216 minus 2, and outer side will be 13, right? To solve this entire equation, I'll be getting 216 minus 3 plus 4 216 minus 3. Okay, there's one more 216 here, and there's 216 here also, right? So if you solve these 216 together, it will be coming to minus 29. Please solve it down on your own and then see what is the value. This is what you're going to get. Okay, this is minus 29. Further solving this, which one is the smaller value? 216 is the smaller value. Please find out a substitution for 216. This equation will serve as the substitution here, and my value is going to now be 1180 plus 482 minus 2, and there's going to be a value of minus 29, right? I hope you can understand this. Plus to this is going to be as it is, 482 13. After this, when you solve this, you get value as 1180 minus 29 plus 482, and you get 71, and which is equivalent to 2. All these are equivalent to 2, right? Now you got the value. Please see, this equation is similar to this equation. 2 is equal to 1180 plus 482. I've got the value of x. The value of x is minus 29, and the value of y is 71. Okay, so this is how you solve extended Euclidean questions, and there's no other way of asking question. Either they will ask in this elaborate manner, find linear combination of two integers which is equivalent to GCD, or they will be asking you to find extended Euclidean algorithm of two integer, which is just the straight away mentioning of the standard formula, right? Extended Euclidean algorithm. Okay, so moving ahead to the next topic, which is Fermat's theorem. Now Fermat's theorem, also called as Fermat's little theorem, Either you can call it Fermat's theorem, or you can also call it as Fermat's little theorem. They are one and the same. Now, Fermat's theorem or Fermat's little theorem. Now, what does this theorem state? This theorem states that, see, if P is prime and A is a positive integer which is not divisible by P, remember, if P is prime and A is any positive integer which is not, remember, A should not be divisible by P, this is another condition, then Fermat's theorem states, Fermat's theorem or Fermat's little theorem states that A to the power P minus 1 is congruent to 1 mod P. Okay, so always remember, if in exam, in case you're asked, please state what is Fermat's theorem or Fermat's little theorem, your answer is going to be that if P is prime and A is any positive integer which is not divisible by P, then A to the power P minus 1 is congruent to 1 mod P. One more condition here, A and P both are relative prime. Now, for what do I mean by relative prime? By relative prime, I mean the GCD of A and P is going to be equivalent to 1. Okay, so this is how you can state Fermat's theorem, and the entire definition, there should be no modification in the definition. This should go exact the way it is written here. Okay, so Fermat's theorem states the following: if P is a prime number, A is a positive integer which is not divisible by P, then A to the power P minus 1 is congruent to 1 mod P. Okay, and both A and P should be relative prime, or you can say both GCD of A and P should be equivalent to 1. Now I'll be using an example to explain you Fermat's theorem. Let me divide the page into 3 parts so that entire thing is written here so that you can understand. Now, example number 1 that I'm going to do here is 2 to the power 16. For example, in exam you're asked 2 to the power 16, find the remainder, when divided by 17. Maybe this is the question that you're asked. 2 to the power 16, find the remainder when divided by 17. Now, 2 to the power 16 is a big value, right? And you have to find out its remainder. How will you do it? See, always I told you, if you remember modular exponentiation. If you remember modular exponentiation, I told you that you have to see what if the divisor that you're dividing by is a prime number, that then you can use Fermat's theorem, and so is the condition here. Here, to the power 16 mod 17. This 17 is a prime number. Therefore, since it is a prime number and here A is a positive integer, right? Here my P is equal to 17 and my A is equal to 2, as you can see from the question, right? My A is equal to 2. Therefore, I can, one more thing that you have to see, whether the prime number P or A should not be divisible by P. A should not be divisible by P. 2 is not divisible by 17, correct? So this condition is satisfying. Moving ahead, both A and P should be relatively prime. Are they relatively prime? Yes, they are relatively prime, because the greatest common divisor between 2 and 17 is just 1. So we can move ahead. Now it is very simple. Now, since all the conditions are satisfying here, we can simply write this in this form. Okay, so 2 to the power P minus 1 is 17 minus 1 is congruent to 1 mod P, that is 17 in my case. So 2 to the power 16 is congruent to 1 mod 17. Therefore, the answer to what will be the remainder when divided by 17, and answer is 1. 1 will be the remainder, as you can see from here, right? So this is easy. Once you see that the modulus part is 17, or once you see that the modulus part is a prime number, then the thing is very easy. But always remember that it should meet 2 conditions, that A should not be divisible by the prime number, and both the prime numbers and the positive integer positive integer, both of them should be relatively prime. That is, their GCD should be equivalent to 1, right? So now moving ahead. Okay, you can also check for this, the validity of this question can be checked by a modular exponentiation method that we did in the last video. Okay, so I'll leave that part to you for checking. Please check with the modular exponentiation, and in case you have problem, please let me know. I'll be doing another video for that. Okay, so next example that I'm going to take is, my next example is 2 to the power 50. Find remainder when divided by 17. When divided by 17. Okay, not always the question is asked in this form. Sometimes the question is asked in this form also. Please note this. Let me demarcate it by some other color so that you can understand. Least, the question is also asked in this form. Least residue in modulo 17 of 2 to the power 50. Right, this the question can be asked in this form also. That is, find out least residue in modulo 17 for 2 to the power 50. Okay, and this question can also be asked in this form. Find out the least residue in modulo 17 of 2 to the power 16. Okay, so please remember this form. This form is also for finding out a value of a modular exponentiation value. Okay, since now we are going to see the modulo part. Here also modulo part is prime number. The p part is actually equivalent to 17, right? And my integer part is 2 here. And since as you can see here, p is 17 and a is 2, and both of them are relatively prime, and 2 is not divisible by 17, therefore we can carry therefore we can apply Fermat's theorem here, and by this we know that 2 to the power 16 is congruent to 1 mod 17. Okay, so from this we can at least conclude this. Now my question is not finding out 2 to the power 16, right? My question is not finding out the least residue in modulo 17 for 2 to the power 16. It is for finding out 2 to the power 50, least residue in modulo 17 of 2 to the power 50. But what you have got is that 2 to the power 16 when divided by 17 is going to give me residue as 1. Now my purpose will be, for power 50, if I can somehow write 50 in terms of 16, if somehow I can write 50 in terms of 16, how can I do that? Now 16 ones will be 16 itself, 16 twos are, no, 16 threes are. When I mention 16 threes are, it is 16 threes are is equal to 48, right? That is something nearest to 50 and not equivalent to 50, because you cannot get 50 by 16. Okay, so 16 into 3 will give me 48. If you do plus 2, you're going to get exact 50. Okay, right. So why am I doing this? Because I know for 2 to the power 16 my residue is 1. Okay, so you can write 2 to the power 50 equal to 2 to the power 16 into 3 plus 2. Is there any doubt in this? I hope not. Okay, so for 2 to the power 16, you can write this as like this: 6 to the power 16 whole to the power 3. Okay, any doubt in this? And then you can write 2 to the power 2 for whole. This is going to be mod 17. This is how you can write. And for this 2 to the power 16, I know the answer is going to be 1, and for 1 to the power 3 is equivalent to 1. Therefore for this I am going to get 1, entirely 1. And for 2 to the power 2, which is 4 mod 17. 4 mod 17. Now for 4 mod 17, what remainder are you going to get when you divide 4 by 17? The remainder is 4. So the answer for this is, the least residue here is 4. Okay, did you see the easiest thing here? I just found out for which value of 2, for which power of 2 I'm going to get residue as 1. That I easily did with Fermat's theorem. After finding out that, I broke my power value into term for which the residue was 1. So 16, for 16 the residue was 1. So basically I decided that 16 if I multiply 16 by 3, I'm going to get a value near about and less than 50, which is 48, and to that if I add 2, I'm going to get exact value of 50. So now 2 to the power 16, I knew that the residue is 1. 2 to the power 16 mod 17, I knew that the residue is 1. And 2 to the power 16 mod 17 is 1. For 1 to the power 3 mod 17, the residue again will be 1, because 1 to the power 3 is equivalent to 1. So this is negligible. After doing this, 2 to the power 2 will be 4. 4 mod 17 is going to give me back the value as 4. So the answer for finding out least residue in modulo 17 of 2 to the power 50 is 4. Okay. Now I am going to do one more example so that you can be well versed with Fermat's theorem and you have no doubt left out. Now another question is, example is 4 to the power 532. Right, I am given, find the remainder when 4 to the power 532 is divided by 11. Okay, is divided by 11. Very simple. Please see if 11 is prime. Yes, 11 is prime. Please see if 4 is divisible by 11. No, it is not divisible by 11. Also see that if 4 and 11, if 4 and 11 both are relatively prime. Yes, they are relatively prime, because the greatest common divisor of 4 and 11 is going to be 1. Okay, so A is 4, P is 11. Moving ahead. Since this is true, I'm going to write down my value from this Fermat's theorem, which is a to the power p, which is 11 minus 1, is going to be congruent to 1 mod 11. So 4 to the power 10 is going to be equivalent to 1 mod 11. Okay, so this means when you divide 4 to the power 10 by 11, you're going to get residue as 1. When you're going to divide 4 to the power 10 by 11, you're going to get residue as 1. Okay. Now my next thing will be, since I know this, I'm going to divide my 532 such that I get 10 value. Okay, so very simple. 10 into 53 will give me 530, plus 2 is going to give me 532. Okay, simple. After doing this, you can write it like this. Okay, and then what we'll do, we will write 4 to the power 10 to the power 53 into 4 to the power 2 mod 11. This is entirely going to be 1, right, plus 4 to the power 2, which is going to be as 16 mod 11. Now 16 mod 11, when you divide 16 by 11, what is going to be the residue? The residue is going to be 5. So the answer is 5 mod 11. Therefore for this, my answer is 5. Okay, see, such a huge number, 4 to the power 532. What residue are you going to get when you divide 4 to the power 532 by 11? The simple method, and the answer is 5. Okay, so I hope you're well versed with Fermat's theorem. Okay, there is another version of Fermat's theorem that you must know. There's another alternate form of Fermat's theorem. Okay, so the alternate format of alternate form of Fermat's theorem states that if P is prime and A is a positive integer, then you can state that A to the power P is congruent to A mod P. This is another theorem that you can use. Just remember one thing, that here for A and P, it is not necessary that they are relative prime. For A and P, not necessary that they should be relatively prime. Okay, so this is another alternative form of Fermat's theorem. Always remember, if in exam it is asked what is the alternative form of Fermat's theorem, this is the alternative form of Fermat's theorem, which says if P is prime and A is a positive integer, A to the power P is congruent to A mod P. And for A and P here, it is not necessary that they should be relatively in prime. Okay, I'll also be doing a question for you so that you can understand. Just assume that P is equal to 5 and A is equal to 3. For this, you can see that you can write A to the power P as 3 to the power 5, which is 243. Right? For 243, you can write 243 is equal to or is congruent to 3 mod 5. Okay. Which is, if you can see from this equation, it is equivalent to A mod P. It is not necessary. Remember, it is not necessary. This is not compulsory condition. Okay. If it is existing, there's no issue. If A and P are relatively prime, there's no issue. But this should not be necessary condition for alternative form of Fermat's theorem. So moving ahead, coming to my last topic, which is Euler's theorem. Very interesting. To understand Euler's theorem, you have to understand what is Euler totient function. Right. So before presenting Euler's theorem, I'll be discussing what is Euler's totient function. Now, you represent Euler totient function by this phi n. You represent Euler totient function by phi n. Okay. Here, if n is a positive number, then this phi function helps you in counting. The positive integers that are less than n, that are relative prime to n or co-prime to n. Okay, so can you understand this? See, again I will tell you, phi helps you in counting. All the numbers that are less than n and that are relative to n. For example, if I say phi 10. Now, what are the numbers that are less than 10 and are relatively prime to 10? What are the numbers? Numbers will be 1 and 10 GCD is simple 1. Okay, 3 and 10 GCD is simple 1. Okay, 7 for 7 and 10 GCD is simple 1. Then 9 for 9 and 10 GCD is simple 1. Okay, so these are numbers that are relatively prime and they are less than 10. So how many numbers are they? They are 4. So phi helps you in counting how many numbers are less than 10 and are relatively prime to 10. So the answer for phi 10 is 4. Okay, I'll do one more question. Phi 7. For phi 7 the answer is 1 is relatively prime to 7, 2 is relatively prime to 7, 3 is relatively prime to 7, 4 is relatively prime to 7, 6 is also relatively prime to 7. So how many numbers? 6. The count is 6. Okay. There are 6 numbers that are less than 7 and that are relatively prime to 7. Okay. All the numbers less than 7 are equal are relatively prime to 7. Now there are certain properties that are associated to it. Now if p is a prime number, then phi of p is just one value less than p. As you can see here, p here my p was a prime number, 7 was a prime number, and phi p, the value of phi p was just one less than the 7. As you can see here, right? Here the prime numbers were 1, 2, 3, 4, 5, and 6. That is, the counting is 6. Okay. So the first property is phi p is equal to p minus 1 if p is a prime number. Okay, for phi 1, if you are supposed to find out the phi 1, then the answer is always 0. Always remember this. Now the third property says that phi m cross n, you can write this as phi m into phi n. Here m and n both are relatively prime. Here m and n both are relatively prime. I can also take up an example for this. For example, phi 35. Can you factorize this into prime factors? Yes, you can. That is 7 and 5. So phi 7 into 5. Okay, so you can write this as phi 7 into phi 5. And the value for phi 7 is 6 and the value for phi 5 is 4. So 6 into 4, that is going to give me 24. So phi 35 is going to be 24. This is the third property here. Okay, another property is phi of p, that is prime number. P here is a prime. Phi p to the power e is always going to be equivalent to p to the power e minus p to the power e minus 1 if p is a prime. Okay, this is another property that you must remember. Okay, so I'm done with Euler-Tauschen function. Always remember, Euler-Tauschen function gives you count of relatively prime numbers that are less than n. Okay, moving ahead to Euler's theorem. Now, what do you mean by Euler's theorem? Euler's theorem is just the generalization of Fermat's theorem. Okay, it is just the generalization of Fermat's theorem. And just remember, in Fermat's theorem, the modulus was supposed to be prime, but here that is not a necessary condition. Here, the modulus in Euler theorem must be an integer, must not be a prime number, must be an integer. Okay, now what does it state? If I have to state it in a definition, it is if a and n are relatively prime. If a and n are relatively prime, then if we multiply a with itself phi n times and divide the result by n, the remainder should be 1. See, this is what I've written. Mathematically, if you have to write, you can write it like this. This is how you state. Okay, let me once again help you to understand the concept of Euler's theorem. Euler's theorem states that if you multiply a by phi n times by itself, then it is going to be congruent to 1 mod n. That is, if it is going to be, if a is divided by phi n times by itself, then when you divide n to a phi n, it will give you residue as 1. That is the definition. Always remember, here a and n should be relatively prime. Okay, a and n should be relatively prime, but for n it should not be a prime. That is not necessary that n should be a prime number. Okay, I hope you've understood this. Let me take up a question for this. For a is equal to 11, suppose if I have a is equal to 11 and I have n is equal to 12, right? And both for 11 and 12, as we can see, the GCD, the greatest common divisor, is 1. Okay, so moving ahead to phi n, that is phi 12. The value of phi 12 is going to be it's going to be 4. You can also do it easily by factorizing 12 into its prime factors, and then for prime factors, it is just Tauschen function is just one value less than this. Okay, So here the torsion function for 12 is 4. Why am I finding the torsion function? As you can see here, phi n is to be found out. Now after doing this, I'll be writing down my equation for A11 is equal to the power of phi 12 is going to be congruent to 1 mod 12. Right, this is how you can write. So 11 to the power 4, as we found out, is congruent to 1 mod 12. Right, so 11 to the power 4, if you elaborate, if you find out the value for 11 to the power 4, it will be 14641, which is going to be congruent to 1 mod 12. Right, so I hope you've understood Euler's theorem. As we have seen that for Fermat's theorem there was an alternative form. Similarly for Euler theorem also there is an alternative form. Euler's theorem says Euler's theorem for alternative Euler's theorem states that if a and n, if you know a and n are not uh, relatively prime, if a and n are not relatively prime, for that condition also you can mention Euler's theorem, which says a phi n plus 1 should be congruent to a mod n. Okay, this is the condition when a and n are not prime, not necessarily prime. Okay, so this is an alternative form for Euler's theorem. So I'm done with my lecture 4, which is very informative. Please stay tuned to all the lectures that are going to come ahead. Thank you so much.